Hey everyone, this is Mr. Bowman, and in this lesson I'm going to show you how to use synthetic division to reduce higher degree polynomials down to factorable quadratics or quadratics that you can apply the quadratic formula to find the irrational zeros. Now, you might recall that rational numbers or rational zeros are numbers that can be written as the ratio of two integers. Like 5 could be written as 10 divided by 2, or 3/4 is 3 divided by 4. So we're going to start out using the given information here about two of the rational zeros. And that's in the form of this hint. We're told that f of 4 is equal to 0, which means x equals 4 is a 0 of this polynomial. And we're also told f of negative 1/2 is equal to 0, which also tells us that x equals negative 1/2 is a 0. So we'll do synthetic division twice on this fourth degree polynomial and reduce it down to a second degree polynomial, which we can either factor or use the quadratic formula on. So let's get started. We'll put one of the zeros on the shelf. We'll start with 4, put the coefficients of the fourth degree polynomial up here. Make sure that you've got all of them. And since 4 is known to be a 0, when we get done with this synthetic division, we should get 0 as a remainder. So 2 comes down, 4 times 2 is 8, negative 7 plus 8 is positive 1. 4 times 1 is 4, negative 14 plus 4 is negative 10. Negative 10 times 4 is negative 40. 35 plus negative 40 is negative 5. 4 times negative 5 is negative 20. 20 plus negative 20 is 0. So far, so good. We're going to put negative 1/2 on the shelf and do synthetic division again. And again, we should end up with a remainder of 0. Not there, where I first drew it, but there. So let's see what we get. 2 comes down. 2 times negative 1/2 is negative 1. 1 plus negative 1 is 0. Negative 1/2 times 0 is 0. Negative 10 plus 0 is negative 10. Negative 1/2 times negative 10 is positive 5. And negative 5 plus 5 is 0. So at this point, we have the coefficients of the quadratic, and they are 2, so 2x squared, plus 0x minus 10, and we want to factor it. So we set that equal to 0. Normally, I wouldn't write it like this. I would drop the 0x, so we would write this as 2x squared minus 10 is equal to 0. But if you don't see how to factor this, you could always apply the quadratic formula. We can factor a 2 out. So we have 2 times x squared minus 5 is equal to 0. And at this point, you have to factor it, or you have to go back to the original form right here and use the quadratic formula. So this x squared minus 5 is actually the difference of two squares. You just have to figure out what you square to get 5. And it's the square root of 5. So this factors into 2 times x plus root 5 and x minus root 5, which means that our two irrational zeros are the square root of 5 and the opposite of the square root of 5. So this original polynomial, f of x, I believe it was called, in factored form is going to be x minus 4, x plus 1/2, x plus root 5, x minus root 5, and then we've got that 2 out there in front of the very last factored form. Okay, so now to the reason why we factor this. We factor it so that we can graph it easily. So we know that there's a 0 at positive 4, 1, 2, 3, 4, and it has multiplicity 1, so our graph is going to cross there. We know we have a 0 at negative 1/2 with multiplicity 1, so we know our graph is going to cross there. We also know we have zeros at plus or minus root 5. So I don't know exactly what the square root of 5 is, but I know that it's between the square root of 4, which is 2, and the square root of 9, which is 3. So somewhere between 2 and 3, we've got a 0 of multiplicity 1. And so our graph crosses there, and -2, -3, somewhere between -2 and -3, we'll have another 0 with multiplicity 1, so our graph crosses there. Now, what else could we do? We could find the y-intercept. That's going to be easiest to do by going up to the top and plugging in x equals 0, and our y-intercept is positive 20. So way up here at positive 20, 0, 20, we have a y-intercept. And we have a fourth degree polynomial with a positive leading coefficient, so we know our end behaviors are going to be both towards positive infinity. So what has to happen? The graph has to come down, it has to cross, has to go up and grab that y-intercept, it has to come down and cross, and like that. And so that's the general form for our fourth degree polynomial. And remember, the reason we factor it is so that we can accurately graph it. One last comment about this example. If you did not see how to factor this, you can always use the quadratic formula. And since we have in the line above, which I will highlight, we have the quadratic in standard form, we can find that a is equal to 2, b is equal to 0, and c is equal to -10. And you can plug that into the quadratic formula and simplify, and then figure out what the zeros are, and from there you can find that the factors are x plus root 5 and x minus root 5. I just feel like it's quicker to factor if it's something that you see how to factor. All right, for our second example, we're going to have to do a little bit more work here. In this example, we're also given a fourth degree polynomial, but we're not given any of the zeros. So we're going to have to graph this function on our calculator, find the rational zeros, and then use those along with synthetic division to again reduce this fourth degree polynomial down to either a factorable quadratic like the last problem, or use the quadratic formula. So pause the video right now and go ahead and put this function in your calculator, graph it, and then we're going to find the rational zeros. All right, so one of the things you have to do when you're using your calculator is make sure you take your time and get the function put in correctly. Otherwise, everything is going to be all wrong from there. So I've done that here with our second example, and I am going to simply start with a zoom standard and see what we can see. Okay, this is good. What I see is I see 4 zeros, and they all look like they're multiplicity 1, which they would be if there's 4 different zeros with a fourth degree polynomial. Let's use the zero function to find 2 of the rational zeros, and then we'll do synthetic division with those to find the irrational zeros. So I'm just going to start at the left-hand side using the zero function. And let's see, I'm going to trace over here to my left bound of -4, should be good. Yep, and then in between, there's my cursor, in between those two on the left, that's good. So, first zero is a rational zero of -3, so put that in your memory. And I'm going to guess that the other one is at +2 just by looking at it. So here's a quick way you can check that. If you hit second and the trace button and you use the value feature, if x equal 2 is a 0, y should be equal to 0. So -3, +2 are 2 zeros for our fourth degree polynomial. And now we're going to use those to do synthetic division. All right, so I'm going to start with -3 on the shelf. Our coefficients 1, -5, -31, 17, and 114. Again, if -3 is a 0, then we should have a remainder of 0 here. So let's see what we've got. We've got 1 comes down, -3 here, so we get a -8 here. So we get a 24 here. So we get a negative 7 here, which gives us a positive 21. 21 plus 17 is going to be 38. Let's see, 3 times 30 is 90. 3 times 8 is 24. 90 plus 24 is 114. So negative 114. And we are good. Now we're going to put positive 2 on the shelf. Do the same thing. We should get a remainder of 0. 1 comes down. 2 times 1 is 2. Negative 8 plus 2 is negative 6. 2 times negative 6 is negative 12. Negative 7 plus negative 12 is negative 19. 2 times negative 19 is negative 38. And now we have 0 for a remainder, which reduces the polynomial down to a second degree, and its coefficients are 1, negative 6, and 19. And if we set that equal to 0, we can use the quadratic formula or factor it. It is not factorable, so we are forced to use the quadratic formula here. Our quadratic's in standard form, so we have coefficients a equal 1, b equal negative 6, and c equal negative 19. And so what do we have? The opposite of b is 6 plus or minus the square root of b squared, 36, minus 4 times a times negative 19 all over 2a. So we have to do a little bit of simplifying here. As you can see, I needed to write 1 in place of a, and I didn't do that, so we've got just a 2 down there. So let's start simplifying. 6 plus or minus the square root of 36 plus 4 times 19. 4 times 19 is hard for me, so I just do 4 times 20, which is 80, and subtract 4, so that's 76. Divide that by 2. 6 plus or minus 36 plus 76 is going to be 112 divided by 2. Now I got to see if I can factor out a perfect square out of 112. After a little bit of experimenting, you can probably figure out that you can factor out 16. So 7 times 16 gives us 112 divided by 2. So we can now write this as 6 times plus or minus 4 root 7 all divided by 2. Remember, you can only cancel out what you can factor out of the numerator and denominator. So you can factor a 2 out of the numerator and denominator, so you get 3 plus or minus 2 root 7 all divided by 2. The 2's cancel out, so you get zeros of 3 plus or minus 2 root 7. Alright, what does that mean? That means that our polynomial, our fourth degree polynomial, factored into x plus 3, because negative 3 was a 0, x minus 2, because 2 was a 0, x minus each of these irrational zeros. I like to write these in parentheses. 3 plus 2 root 7, and x minus 3 minus 2 root 7. All right, and the whole goal of all of this is so that we can get a reasonable graph of this polynomial. So again, we've got a 0 at negative 3, multiplicity 1. We've got a 0 at positive 2, multiplicity 1. 3 plus and minus 2 root 7. All right, we're going to have to estimate this. Root 7 is between root 4 and root 9, so it's between 2 and 3. So let's estimate 2.5. So 2 times 2.5 is negative 5. 3 minus negative 5 would be somewhere around negative 2. I'm just going to estimate that there. And 3 plus 5 would be somewhere around positive 8. So 2, 3, 4, 5, 6, 7, 8. Again, I'm estimating where those are at. And if we go back to the original form, we can easily figure out that the y-intercept f of 0 is 114. So we're going to have across the y-axis way up here at 0, 114. And it's a fourth degree polynomial with a positive leading coefficient, so the end behaviors are both to positive infinity, and each of our zeros have multiplicity 1, so our graph is going to come down, do one of these, do one of those, and do one of those. And you can actually go back to the calculator and verify that we've got a reasonable graph on our calculator. And that's what it looks like. So that's how you factor polynomials that have irrational zeros. You use the rational zeros, use synthetic division to reduce it down to either a factorable quadratic like the first example, or a quadratic where you use the quadratic formula.